Okay, so for number 6, we're trying to create a box that has the minimum cost. So we need an equation for the cost, and we need to derive it to find the minimum. So to begin, we're going to draw the box. Okay, we're going to use wood for the sides and gold for the top and bottom. Doesn't really matter too much right now. And we know the box has to have a square base, which means the length and width have to be the same, and it's got to hold 8 cubic feet. Cubic feet measures volume, so that's its volume. So we have this box, which I'm going to use my super amazing art skills to draw. And it looks like this. And I know that the bottom has to be a square. So they both have to be the same exact values down there. And the height can be whatever it wants to be. Okay, so the cost of this box is just going to be the cost of all the sides added up. And you can see that the bottom is going to be a W squared, right? That's the area of the bottom. And the top is also going to be W squared. So we're going to have 2 W squareds we have to build. And because those are the top and bottom, we want to use gold for the top and bottom. So each square foot of gold costs $10 per square foot. So that means that if we have to make 2 W squared square feet, we have to multiply that by $10 per every one of them. So that's actually going to be 20 W squared for the cost. Okay. Now, that did not include the sides, so we got to look at the sides. Well, look, this side here has an area of WH. This side here has an area of WH. The area, or the side on the left, has an area of WH, and area on the back is going to be WH. So we really just have 4 WHs that we have to build. But they're going to be made of wood, right? You wood for the sides, yep. And wood cost $1 per square foot. So technically, we got to multiply that by $1 for every single square foot we use there. But that just gives us this. So that's our cost equation. And just like most optimization questions, the problem is we've got 2 variables in there, 2 independent variables, and we got to get it down to 1. So we have to use this restriction, and the restriction was the volume had better be 8 cubic feet. Okay, and all that does is allow us to use a little substitution here. So we're going to say that the volume of this box, which is W times height, has to be 8. That's volume. And that lets me know right there that for the volume to be 8, H is going to have to be 8 divided by W squared. Okay? So this has to happen specifically because of that 8 cubic feet restriction. So that means that the cost is that, let's get rid of all this junk. This is from the last question. Get out of here. Okay? The cost is actually going to be 20W squared plus, if you plug in, so take this H out is what we're doing, and we're plugging in 8 over W squared. A W is going to cancel because you have a W in the numerator, 4W, and a W squared in the denominator, and 4 times 8 is 32. So you're going to get that as your derivative. Oh, not your derivative, as your cost equation as we sub out H. But we want the derivative because we want to know what the minimum cost is. So we're going to do dC with respect to W is equal to 40W minus, so this is W to the negative 1 again, so it's going to become 32 over W squared. And now we want to know what's going to make that 0 or undefined. And to do that, like we said with your derivatives, you want to get a common denominator. So the denominator is going to have to be W squared. So I need to multiply the denominator by W squared. And if I multiply the numerator, there's already a W there, so that becomes W cubed. So the derivative of cost with respect to W is actually 40W cubed minus 32 over W squared. I need to know where that's going to be 0. You can see W being 0 makes it undefined. But W being 0 doesn't make any sense because that means our width would be 0 and we wouldn't have a box. So that's just our least value on our sign chart. So we need to know what makes the numerator 0. And that boils down to 40W squared has to be 32. Oh, W cubed, I mean. W cubed, ugh, get out of here. W cubed has to be 32 over 40, which is 4/5, which means W is the cubed root of 4/5, and that's going to be in feet, I believe. Okay, so we're going to make a little sign chart for this. 0 is the least that it could be. The cube root of 4/5. I have no idea what the cube root of 4/5 is, but I know that like 0.01 is less than it. So I'm going to plug 0.01 back into my derivative up here. Okay, if I multiply 40 by 0.01 cubed, that's going to be, whether you know it or not, exactly what it is. It's going to be very small. Okay, so when you subtract 32, that's going to be a negative number. And then when you divide it by w squared is positive. So we have a negative divided by a positive, which makes this negative here, which means the cost is decreasing if w is increasing in this interval. Okay, so if w goes from 0 and you keep making the box bigger and bigger, the cost is going to get cheaper until you get to the cubed root of 4/5. If you plug in a number after the cubed root of 4/5, like 1, you're going to get a positive number, which means the cost is increasing as w gets bigger there. So the least it could be, decreased, is at the cubed root of 4/5. And I think it asks for the dimensions, right? What dimensions will minimize it? So since we know w, h is just this, so I'm just going to drop it right in there. It's 8 over w squared. So h has to be 8 divided by, it's a cubed root and we're squaring it, so it's really 4/5 to the 2/3 feet, like that. And really the best we can do with that is just, since it's a fraction in the denominator, we can just flip it over. That's really 8 times 5/4 to the 2/3 feet. So those are your dimensions right here in this weird little box.